Hello everyone. Today we are discussing Coulombs Law, which is the force between electrical charges. And Coulombs Law has three essential features that describe the forces between electrically charged particles. And with this, I want to introduce an important equation that helps us calculate quantitatively the forces between charges using Coulombs Law. And it is best denoted by this first point here. The magnitude of the force is proportional to the product of the charges and inversely proportional to the distance between the particles. So the magnitude of the electric force, denoted by F electric, is equal to the product of the charges, so Q1, this would be charge 1, times the charge 2 of Q2, divided by r squared, which is the distance between the particles squared. And it's important to recognize the relationship between these variables. So if I were to say that Q2 increased by a factor of 2, what would we then say happened to the force between the electrical charges? Well, if Q2 increased and everything else was held constant, the force between the two charges should increase by a factor of 2. Let's consider the distance. If the distance were to increase, so if r squared were to increase by a factor of 2, what would happen to the force? Would it increase by a factor of 2? Would it increase by a factor of 4? Decrease by a factor of 2? Or decrease by a factor of 4? Well, we know that r squared is in the denominator, so we know that since these are inversely proportional, increasing r squared would decrease the force, so these two are out, and we know that an increase of r by a factor of 2 when squared becomes a factor of 4, meaning that when you double the distance between the two charges, the force actually decreases by a factor of 4. And this is important to understand because when considering this equation, we can do this vice versa. We can say, what were to happen to the distance between the charges if the force was to decrease by a factor of 4? So if everything else was held constant, what would happen to the distance if force was decreased by a factor of 4? Well, then we would know if it was decreased by a factor of 4, r must have increased by a factor of 2. Therefore, that's why this relationship is important to understand, because then we can manipulate this equation and find the relationships between each of these variables in this equation. But moving on, let's consider the two other important features of Coulombs law. The direction of the force is along the line connecting the particles. So we can say that we have two particles here. The direction of force is literally the shortest line that connects the two particles. And then 3, the direction of force is attractive for opposite sign particles. So protons and electrons are oppositely charged and they're attracted toward one another. And then like sign particles, so 2 electrons or 2 protons, are repelled by one another. And that's pretty straightforward stuff. So let's get started with our questions. 2 uniformly charged spheres are firmly fastened to and electrically insulated from frictionless pucks on an air table. The charge on sphere 2 is 3 times that of the charge on sphere 1. Which force diagram correctly shows the magnitude and direction of the electrical forces on the spheres? So there's a couple things to keep in mind with this equation, or this question. Firstly, all of these spheres are positively charged, and we have to recall that like charges are repelled by one another. So like charges repel one another. So when keeping this in mind, we know that any of these spheres that have the same directional motion are incorrect. So B and A are incorrect because they are not repelling each other. They are going in the same direction, which is not a characteristic of like charged spheres. Moving along, the second thing that's important to keep in mind is the keyword electrical forces. So we have to recall and remember that electrical charges and electrical particles are still undergo Newton's laws of motion. Specifically, what's relevant here is Newton's third law of motion, which states that for every action there's an equal and opposite reaction, meaning that the force that sphere 2 imposes on sphere 1, so this would be force of sphere 2 on sphere 1, is equal to that of the force of sphere 1 on on sphere 2. So that means that the magnitude of the forces between sphere 1 and sphere 2 acting upon each other should be in opposite directions and equal to one another. So these hash lines mean that they're equal, if you remember geometry. So keeping that in mind, when we're considering the remaining answer choices, we see that C says that the repulsion of sphere 2 is greater than that of sphere 1, but that doesn't fall in line with Newton's third law of motion, so it's false. E is a bit tricky because it may go along with your intuition that, oh, look at it, it has a longer force associated with it because it has less of a charge. It's getting repelled more because sphere 2 has a greater charge. But we have to remember that even though it has less of a charge, the force between these two spheres is the same. So that is why E is also false. And D is the answer because these spheres are, the magnitude of the forces on each of these spheres is equal to one another, which is in line with Newton's third law of motion. And they are in opposite directions, which is in line with our understanding of like sign electrical particles. So next we have 3-15C, which says, which arrow represents the direction of the force on the charge at the top due to the two charges below? So it's asking, what is the net force that particles 2 and 3 act on particle 1? So we specifically have to recall that it looks like, it seems as though, particle 2 and particle 3 have an equal charge to them. They're both positive 1q and negative 1q. And then we don't know the charge on this specific particle here, particle 1. However, that's not relevant specifically to this question because the charges acting on it are equal. So we have to first look at the charges that are acting on it. And particle 2 is a like sign to particle 1, meaning that the forces acting on them are repulsive and in opposite directions. So particle 2 would be repelled away from particle 1, and particle 1 would be repelled away from particle 2. Likewise, if we're considering particle 3 and particle 1, we have to keep in mind that these are like charges, and since these are opposite charges, not like charges. And since these are opposite charges, they are attracted toward one another. And presumably, since these look pretty equidistant to particle 1 here, we can say that the forces in these directions are equal because the charges are equal between particles 2 and 3. It's just that the direction is not. So if we know that the hypotenuse of each of these is the same, we can then assume that the one of the legs of this triangle, if we were to make this a triangle, we can say that the vertical forces cancel out because this would be negative x and this would be positive x. So we know that the net force would then be the sum of the horizontal forces, and since those are both in the same direction, which is positive y, let's just say it's positive y, this would be D overall. So that is why D is the answer, because the repulsive forces between like charges repel particle 1 away from particle 2, but the attractive forces between opposite sign charges, particles 1 and particle 3, attract these two particles together, which then causes the forces between these two particles on particle 1 to cancel out in terms of vertical vectors, meaning that D is the answer because the horizontal components of these vectors actually add to one another. So yes, that is why D is the answer. So the next question that we have here is, which of the three charges on the right or below experiences the largest force? So if we recall, we just analyzed this equation. The force of the electric charges is equal to the Kc constant times the product of charge 1 times charge 2 divided by the distance squared. So this is a qualitative question, but we can kind of input the changes into this equation here. So I've done the liberty of doing this for us. So for this first set of charges, we see that the force, so the force is equal to the Kc constant times 1q, so 1q1, so that's q1, and then times q2, and q2 and q1 both have a charge of positive 1, divided by 1r, because we have a distance of r. And then if we look at the second one, we know that we see that the force is equal to the Kc constant times charge 1, which has a charge of positive 1, times charge 2, which has a charge of positive 2, so 2q, divided by a distance of 2r, so 2r squared. And then we have the third set of particles here, and we have charge 1, which has a positive 1 charge, and charge 2, which has a positive 4 charge. So the force would be equal to Kc times, so let's just imagine for a second that this is on the numerator. Actually, I can do that. So time is equal to Kc times charge 1 times charge 2. So charge 1 has that positive 1 charge, and charge 2 has a positive 4 charge, divided by the distance squared. So if we were to simplify this, we see that the force acting between these particles is equal to, the force is equal to q over r. And then for the second one, it would be 2q over 4r squared. So this is r squared as well, sorry. Which then becomes q over 2r squared. And then this final one is the force is equal to 4q squared, so these are all squared as well, over 4r squared. And simplifying this further, we see that q squared over r squared is equal to the force. And when looking at these values at the end, these qualitative values, we know that this is the smallest because the overall, whatever overall value we have here is divided by a factor of 2. So it's being divided by a factor of 2 because 2 is in the denominator, compared to these two other equations which don't have that, meaning that set 1 and set 3 have the largest force, meaning that E is the answer. Q would be true if the distance between between these two particles in equation or in scenario 3 were farther, or if the distances between the two charges in scenario 1 are shorter. There's a billion ways that you could make Q, this scenario here, scenario 1, have a larger force than scenario 3, but these two have equally large forces on one another. B is not true because of we had discussed the factor of 2 that decreases the force by a factor of 2. And then 3 is technically true, but the best answer is 1 and 3 because they both have the same forces acting on this particle here. So that is why E is the answer. Finally, we have 3-15E. In each of the following cases, an identical positive test charge is placed on the black dot. So this is a positive charge in each case. In which case is the magnitude of the net charge the largest? So the best way to analyze this question is by drawing out the force diagrams, and I'm doing this in the color red. So we have to remember that like signs attract and opposite signs repel. So keeping that in mind, let's look at all the options. So we have option A here, where we have a negative charge that attracts the positive charge, and we have a positive charge that repels the equally positive charge. And we have to keep in mind that these are equidistant to one another. So the forces between these two particles on this test black particle, are the same, and they're both in the same direction, which would then mean that the force is 2 of this. So it's just twice as long. So we can say that the overall force on particle in particle A is twice as large. We can just make it twice as long. So looking at B here, we see that we have an attractive force toward this first closer particle, and then we have a repulsive force, but that repulsive force is farther away. So this is essentially double the distance away, 2r. So it would have a force that is 1/4 that of the force between this negative charge here and the positive test charge. So that means that if we were to consider the overall charge on this black test charge, it would be somewhat less. So it'd be like something like this, relatively speaking. If this was 4, this would technically be 3. And then moving along, we have the positive charge here, and we see that the positive charge is being repelled by both charges here. So we can say that this positive charge is getting a force, the first force by this closer one. This closer positive charge repels it a distance away, and then the second charge here repels it, but the force acting between these two charges is less because of that distance. So this is 2r distance away, meaning that the force acting on it is 1/4 that of the force of this first charge here. So it's a smaller charge. So if we were to consider the overall charge, it would be greater than B, but it would be less than A. So we could say that if the force between particle positive particle 1 is 4, and the force between the second positive particle and the test particle would be 1. So if this was 4 and this was 1, it would be a sum of 5 to the left. So, and then coming back up to A, we would say that since these are equidistant, and these have equal forces, we could say that this is 8 and to the right. And then finally we have D, and this positive test charge is being pulled on in both directions by the negative charges. So we know that since these are equidistant, they're acting equally on this particle. So this first negative charge is pulling the positive charge toward it, and the second negative charge is pulling the positive charge toward it. And they're acting in opposite directions, and they're equidistant, so the forces are equal, meaning that the overall charge is 0, or the overall force is 0. So there's a 0 net force, meaning that there is no overall net force acting on particle D. So if we were to consider the magnitude of the charges, which one has the greatest magnitude? A, by virtue of just being the largest, we had arbitrarily decided this was A, or this was that the force was equal to 4, just for simplicity of calculation. A has the largest value here because both forces are equidistant from the test charge, and they both act in the same direction, so they're double, which is why A is the answer. B is not the answer because the negative attractive charge of this closer particle is not enough to the magnitude is not large enough to be greater than that of answer A. Same with answer C. Even though these are both in the same direction, the distance to this farther particle diminishes the force acting on the test particle. And then D, there's no overall net charge, which is why D is false, or is not the correct answer. And that is the final question we have for this practice set. Hopefully you found this helpful. If you did, please subscribe, please like the video, and have a great day.